Can I start?
Yes, you can start. We can see and hear you wonderfully.
Yeah, so last week I ended with vision language action models. And this week I actually want to focus on this type of model and with a particular focus now on cognitive robots. And in robotics, the issue is that data is not as abundant as with other tasks. Yeah, for training, for example, large language models, one finds data, a lot of texts and so on the internet, and then one can try to learn from this. Also with computer vision, as Jürgen Gall just presented, there is a lot of images and text also on the internet, and one can compile data sets and try to learn from that. With robotics, it's a little bit more difficult. And there is, of course, possibilities how to move forward. For example, by transfer learning, meaning that one somehow finds a large related data set where one can learn features from or representations from, for example, with self-supervised learning methods, as I described last week. And then hopefully starting from that, or maybe by continuing training or using the representations, we can somehow capture that knowledge that has been on the large data set and use small data to actually learn what our task is. And of course, I mentioned already last week, generating data is also a possibility. For example, this physics-based simulation, we can generate a lot of synthetic experience, but is that like the real world? Yeah, so we have some sim-to-real gap there usually that we need to address. And I had 2 slides last week also on inductive biases, by incorporating some knowledge about the world or the problem at hand, and maybe restricting what we can learn, but then have fewer parameters, faster inference, and we need less data. So these are possibilities, and why is it actually so difficult with robots? Yeah? So if we want to learn, for example, a simple Atari game like Breakout, this can be done with limited experience. But if we want to play, for example, this game, which is somewhat more complex, Montezuma's Revenge, then this is like almost impossible with current methods to learn. And why is this the case? Well, there is many aspects of that game. Yeah, so for example, when we have such a key, then we are rewarded in some way. Maybe we can open a door, and when we open a door, that means we have to key and then maybe find the door. We are rewarded as well. And maybe when we encounter such a skull, then this would be very bad. And the thing is that we as humans know what to do in such a game, because we understand already what these sprites mean. So we do not start learning from scratch here, but all the experience that we accumulated over our lifetime helps us to somehow play that game and quickly learn then what to do in Montezuma's Revenge. Yeah, so we know that keys are used to open doors, and we know that we can climb ladders, or that probably a skull doesn't mean anything good here. And yeah, this world knowledge that has been somehow accumulated in our brain helps us to solve new tasks quickly. Yeah, so maybe some of you have seen Indiana Jones, and then this game has been inspired by this movie and the story, and that's why you know what to expect here and what to do, even though you really haven't seen these situations before in the game. So if we have solved prior tasks, we may have acquired useful knowledge for solving a new task. And then a question arises, of course, is like, how is this knowledge stored? And there might be a queue function. Yeah, so in reinforcement learning, I told you about value last week. Yeah, so that somehow predicts the accumulated reward that usually follows when we are in a particular state, like the probability of winning we had in this tic-tac-toe game. And if we combine state and action, we can represent value in a queue function in a little bit more detail here. And the policy maps actions, maps states to actions. Yeah, so it tells us which actions are potentially useful. We may also learn a model of the world. Yeah, so when we are in this state and we perform this action, what is the probability of a successor state? What could happen next? Yeah, kind of a simulator of the world. And yeah, of course, also some features that may have been extracted from images or some hidden latent representation may be a good starting point for learning, because this might be lower dimensional, or maybe we disentangle certain factors in our distribution and the like. So the situation is that we usually have some source domain, yeah, maybe the movie here, and then we have a target domain that we are actually interested in, and we try using transfer learning to use experience from our source domain to have a better performance, faster learning in the target domain. And in reinforcement learning, usually the task is to solve Markov decision problem. Of course, this kind of assumes that we summarize everything we need to know about the past in the state. Yeah, so that's a convenient assumption here. And of course, if the state is not strong enough, we need to make it stronger so that it actually summarizes everything we need to know. And then we can distinguish the number of shots as the number of attempts in the target domain. Like zero shot means that we just run policy as trained in the source domain. Yeah? So we hope that our source domain is somehow rich enough or variable enough that our task in the target domain is somehow in this distribution. Yeah? But it might also be that we do one shot, meaning that we try the task once, or maybe we get a few shots of making experience in our target domain. And there is different ways we can formulate this transfer learning. Like forward transfer means that we train on a source task and then run on a target task or fine-tune there. And this relies on the task being quite similar, or multitask transfer. We train actually jointly on many tasks and then transfer to new tasks. And that means that we share representation and layers across tasks in this multitask learning, and the new task needs to be similar to the distribution of training tasks. And meta learning is actually learning to learn on so that accounts for the fact that we will adapting to a new task actually during training. And how could this be done? For example, by having different tasks here for this mobile manipulation robot. By the way, this is the famous PR2 that started ROS with Willow Garage, so funded by Google money at the time. And yeah, we don't just learn a single task, but we learn a multitask model. And this then accelerates learning on all tasks that are learned together and provides a pre-training for downstream tasks, yeah, for maybe new tasks that we want our robots to perform. And yeah, this actually means that we do not solve a single MDP that would correspond to a single task, but that we somehow first sample which task to solve, maybe from a common starting state, yeah, and then actually solve that. Yeah, so it's like a larger MDP that we are addressing now. And yeah, the policy can then do multiple things in the same environment, for example. Yeah, so we have the robot, and maybe in one task, is doing the dishes, and in another task, the robot is taking care of the lawn. A standard policy would simply look at the state and then produce the probability of the actions to take here. Yeah, so action selection probability, and that is parameterized by some parameters. Yeah, so often the policy is some sort of neural network, has some parameters, and this is all in this parameter vector here. And we can look at so-called contextual policies, meaning that in addition to the state, we have like a context variable. So you can imagine this to be some sort of a prompt, yeah, or a task description. And that could be in our example, yeah, do the dishes or do the laundry. And then, yeah, we would actually apply the methodology of reinforcement learning, of solving MDPs in an augmented state space. So we take the original state and we augment it with this context variable. And that could be, for example, yeah, a location where we have to place a piece here in this stacking task, or maybe a walking direction where we want this biped to go, or maybe some direction where to hit this hook in this tabletop setting. And we can also use goals, like another state that we would like to have as a context variable. Yeah, so in this case, we would have goal-conditioned policies, and we could say, for example, we reward that our state is the goal state. Yeah, so if we want to reach that state and we actually do that, then we give a positive reward, and otherwise maybe we don't. Yeah, or if we don't can expect that we exactly reach a goal, then we can say, okay, we give a positive reward if we are close enough by some epsilon to our goal, and otherwise we give 0 reward. And this is yeah, a convenient way to express what we actually want and to define rewards in a very simple way, but it's sparse in the sense that we get feedback only when we reach the goal, and all the actions that are done along this way are not rewarded. Maybe they are penalized by some yeah, cost of taking an action, but we get positive feedback here only if we actually reach the goal. And yeah, the good thing about it is we can now simply describe a new task by yeah, defining a new goal, and then maybe our yeah, walking robot doesn't go here, but it goes there, and we have a policy that yeah, somehow moves from where our robot is towards some location in this environment. Yeah, so this is quite flexible, but also not easy to achieve, and of course not all tasks are goal-reaching tasks. Meta learning would yeah, try to learn how to learn, and yeah, if, for example, we have learned already 100 tasks, then, yeah, how can we learn more efficiently? And if we succeed in learning to learn, then, yeah, we can learn new tasks quite quickly. And yeah, we can, for example, learn an optimizer or learn neural network, maybe a recursive one that somehow accumulates a lot of experience, or maybe we learn a representation. So why would that be a good idea? Well, I tried to say it already. So reinforcement learning needs a lot of experience, and especially if we don't have a model how the world works. And that means we need a lot of samples, which usually we can generate only in a simulation and not with a real robot. Yeah, and this meta learner, maybe we can then learn how to learn and learn new tasks efficiently. So what can do a meta learner more efficiently? Maybe explore and yeah, not try out random moves as I described last week, but maybe choose exploratory actions more intelligently. Yeah, or maybe yeah, avoid trying actions that are already known to be useless. Yeah, or acquire the right features more quickly. And yeah, when we look at the vision problem here with supervised learning, we try to map quite diverse training data and then transfer that, what we learned, to test data. And later, we would then have another training set and hope that here for this kind of problem, we then also can produce reasonable answers. One way to look at this is that, yeah, we have just a very small training set, like a few shot training set. And then we have a method to compile that, yeah, maybe in a recursive way, maybe not, to some sort of representation, yeah, maybe weights of a network that maps now a test input to an output on this test set that we hopefully, yeah, generate in a sensible way. Yeah, so supervised learning would map inputs to outputs, and we describe what we want to do through that training set. Now, with supervised meta learning, we have a function that depends not just on the input, but it depends on a training set, maybe these few examples. Yeah, so you can imagine this is a large language model. You give 3 examples of what you want this model to do, and then you give 1 more input, and hopefully the model generates the right output. And then, of course, the question arises, like how to read and process this training set. And yeah, there is, of course, multiple ways of doing it. But the generic learning would say we optimize some loss here by changing parameters of a network. Yeah, so a network that somehow maps inputs to outputs. And what we now do is, yes, we optimize again such a parameter vector, but this parameter vector is used to map our training set to some representation of it, or some weight vector, feature vector, call this as you want, that now parameterizes the mapping from our task here described by the test set towards our output where we measure our loss. And one possibility is to do that with a recursive neural network that generates this description of our training set, and then this description is used in the loss computation for the test set. And for reinforcement learning, we can have a similar approach. In reinforcement learning, we try to maximize expected return. So cumulative expected reward. So all the rewards on average we discounted that we expect from our starting state. And we describe this MDP as a set of states and actions and state transition probabilities and expected rewards for these transitions. So we find some weights that actually are part of this policy, of this action selection, and then we try to have as much reward in the long run as possible. With meta reinforcement learning, we would say, okay, we have our task description in form of an MDP, and we map that through some parameterized mapping, some neural network, whatever, towards some representation that we can use to parameterize our policy. So this is somewhat indirect parameterization now. So we have actually two mappings. So one mapping from our problem to this intermediate representation phi, and then the mapping here from the parameters towards the action selection probabilities of our policy. And if you think about it, with a robot, we would have a distribution of tasks that we train on, and we map these individual tasks using some parameterized function, some neural network to a representation. And this now parameterizes our policy, our action selection. And at test time, we would then choose another problem. And of course, the assumption is that this test problem comes from our task distribution. So otherwise, we cannot hope that whatever we learn from that distribution will apply to our test problem as well. And we describe our test task, and then we can follow the policy. In this video, I hope it will play somehow. It's not very smooth, but it shows a teleoperated robot solving some tasks that we had to show for this semi-final of ANA Avatar X Prize. And why am I showing you this? Because if a human mind is in the machine, then this machine can do amazing things. But of course, there is a lot of motivation for autonomy. You don't always have the operators, and there is issues with privacy. And we also want to understand, of course, intelligence by creating intelligent artifacts. But the challenge really is here that the world is open. So in industrial automation, we can structure everything so that the parts that we pick are here. And then we simply have to perform the same motion all the time. But in the real world, many things happen, and there is a lot of variability that we need to address. And of course, you have seen in recent years that large language models, they can digest a lot of data with very simple architectures that involve this dot product attention mechanism. And then depending on, for example, which word is here at the end of that sentence, then weighted representations of these tokens change rapidly depending on which context there is. And yeah, the general principle of training these models is simply next token prediction. Yeah, so self-supervised loss here, and we can always wait and then see how a sequence of token would continue. And still, this is very powerful because there is a lot of data, and this pretext task actually requires understanding the data. And then we can ask questions like this and get answers that are more or less sensible. Of course, you know, these problems have their issues, yeah, so they are not perfect yet, and maybe never will be. But still, there is a large trend in recent years to go from text to other modalities. You have seen in the previous talk by lecture part of Jürgen Gall, in the vision domain, yeah, there is vision language models where we do not generate maybe just language responses, and where we do not just have input as text tokens, but where we have visual inputs and possibly also visual outputs. And of course, this means that we have to somehow translate our image domain towards the language that this model here, this language model understands. Yeah, so some vision encoder transports then the image content to a language that yeah, this model can understand. And yeah, for example, these vision language models can be trained with pairs of images and descriptions of the image content. And then you see behavior like this one here, where you can give an image and then ask what is unusual about this image, and you get an answer that shows some understanding of why is it yeah, maybe yeah, strange to iron your clothes on the back of a car. And even more recent than the vision language models are vision language action models. So now, yes, often we have visual inputs here and maybe other modalities from the robot as well. And we have to translate these images towards the language that this vision language model understands. Yeah, using a vision encoder here, or maybe pre-trained visual features like Dino. And of course, we can also give a language instruction here that would then, yeah, also be passed through the tokenizer and given as an instruction, as a prompt to this model. And the output could, for example, be changes of our end effector pose. Yeah, so move your gripper a little bit towards the left or the right, or close it and up, down, maybe tilt. So these kind of movements that can be used to control the robot. And why should such an approach work? Well, because these yeah, vision language models, they already know a lot about how the world works. Yeah, so they have seen lots of text, they have seen lots of images, and they somehow understand these commands. And then the only thing they still need to learn is yeah, how to map that to the actions of a robot. And of course, you need data for that. Yeah, and here in this work, OpenVLA, yeah, like roughly 1 million episodes was used from many different labs. A data set called OpenX Embodiment, where you have stationary manipulation robots performing lots of tasks in different labs, different tasks. So you have a big variability there. And yeah, when you then test these models on new tasks, you see that, well, they are not perfect yet, of course, but they somehow generalize to new tasks, to new environments, and you can give instructions like put eggplant into pot, and then the robot is actually doing it, or maybe here with a different object and a different destination. Yeah, so this somehow tries to follow the very same approach that was so successful with the text domain and the text image domain, but with robot data. Or here is a master thesis done in my group of Yao Wang, where he followed essentially this approach, but added one thing, namely a map encoder. Yeah, so in robotics, having spatial representation of the environment is good, and this was about a mobile manipulation task. So here you see how from images and their semantic segmentation, then like a semantic map of this kitchen environment is created. And if you give this as an additional input to this vision language action model, then we have some advantages. And this approach really starts to move towards real world applications. Yeah, so here is an example, quite recent one, from a company called Physical Intelligence. And they use a lot of multimodal data. Yeah, so all kinds of data sets that are somehow related to this domain where the robot is supposed to be used. Multimodal data, but also robot action data that might be collected in the wild or in the lab, and with annotations. And it's a quite heterogeneous mixture of data. And they also structure their model into stages. Yeah, so there is pre-training on this heterogeneous mixture of data and tasks, and then fine-tuned for mobile manipulation. And the stages that I mentioned are high-level semantic actions. Yeah, so for example, pick up the cutting board or rearrange the pillow. And then there is also a low level that runs at a higher frequency and actually generates then the robot motion to realize the sub-goals that are behind these high-level semantic actions. And the architecture would look like this. Yeah? So there is a lot of data that is digested in this model. And of course, they don't start from scratch, but they use a pre-trained vision language model that already knows a lot about the world, much more than this company could have collected themselves. Yeah? And then you have tasks, you have discretized actions, and it's kind of open vocabulary. Yeah, so even things that are not present during the training can be input here. Object bounding boxes can be input here, and you see that there is a large variety of different data that can be digested by these models, including a couple of 100 hours of actual robot experience in 100 different environments. So you need data. Data with robots is very expensive, but we can leverage a lot of other data sources that are already available on the web or elsewhere. And here you see that from this subtask prediction, then flow model is conditioned on that actually generates continuous actions on a higher frequency so that the robot can move smoothly and swiftly. So the model first infers a high-level subtask, kind of an intermediate goal that it pursues, and then predicts the actions with a higher frequency based on this subtask. And after the pre-training is done, then there is also a post-training stage where a diverse set of mobile manipulators is used, where high-level text annotations are used, verbal instructions are used, and other data sources are fed in, so that in the end, a model comes out that can be deployed out of the box in a new home. Yeah, so you can then move that robot to a different place, a different home with different layouts and different objects. But of course, the hope is when you have cleaned maybe 100 kitchens or tidied up 100 bedrooms, you know how to do that when you see environment number 101. And yeah, this kind of works. Yeah, so here, for example, you see some of the actions. Yeah, so like closing the cabinets or putting items in the drawer, or wipe the spill, place the dishes in the sink, and then low-level actions are emitted. The company is using these two mobile manipulation platforms. Yeah, so they are not humanoid robots, but they have two arms and can move on wheels. And yeah, they have their mock-up environments in their own lab, but they also train and test their approaches with real kitchens and real bedrooms outside their labs. And you see here that, yeah, quite interesting long horizon rollouts can be generated in such ways, and that the robot behaves in a sensible way. Yeah, so here, of course, this video is accelerated to not waste too much of your time, but you see how the robot autonomously, just by saying clean the bedroom, then somehow puts away the dirty clothes and tidies the bed and so on. And I find this really quite amazing. I mean, we have been also in the domain of domestic service robots for quite some years. And we have, of course, also shown some interesting demonstrations, but so far we don't have such a big model that can do such a long sequence here and actually do some sensible. Yeah, so I find this quite exciting. And of course, company did also some statistics, and you see that, of course, they don't reach 100%, but their model works quite well. Still, yeah, it only transfers learned behaviors to test environments. It does not know its limitations, so it generates actions even if it doesn't really know what to do. It does not improve from own experience. There is limited context considered. The tasks are also not very complex yet, and human-robot interaction is not addressed. But even more recently, this company announced what they call Pi-Star 06. Yeah, so this is now a vision language action model that learns from experience. And yeah, for example, if you want to learn how to fold such a box, yeah, maybe first you ask someone to teach you the basics, how this box is supposed to be folded. And then maybe a good teacher is actually like a coach and looking what you do and correcting mistakes that you make. And in the end, only own experience, only own practice makes perfect if you really want to optimize how you do that. And yeah, why is imitation not enough? Yeah, so what was done before was simply behavior cloning. Yeah, so do more or less the same as you have seen, interpolate somehow between the examples that you experienced during training. And why is this not enough? The thing is, we have embodied AI here, and whatever our robot is doing will influence what is the input next. Yeah, so of course these models make small mistakes, but then the next input will be different from the situations seen in the training data. And then they make even more mistakes. And then we have compounding errors that lead to these models not being reliable enough yet. And of course, you can say, well, I just need more data. Yeah? But as you have seen with this autonomous driving, even there, you have like 2 degrees of freedom and zillions of data. And yeah, simply cloning people is not enough. Yeah, so the key is really to extract good training samples, signals from bad experience. And the method that physical intelligence proposed recently is called reinforcement learning with experience and corrections via advantage condition policies. And this combines 2 ways to learn. One is coaching, yeah, so to provide corrections when the robot is doing something wrong, then a human expert can say, no, do it in this way. And it uses reinforcement learning from own experience and then improving what the robot is doing by learning what works and what does not work. Yeah, so this is their model. And yeah, on a different computer, everything looks different than on my computer. I apologize for that. But it starts with a pre-trained VLA that incorporates advantage condition. Yeah, so advantage meaning it doesn't really look at the value. It looks at is that more reward than I would expect or less reward than I would expect. And it trains both from these diverse data and corrections and own experience. And yeah, here you see a little bit more detail of this algorithm. So it actually looks almost like before. Yeah, but there is this value model here that is actually a little bit smaller than the big model. And based on that value, then advantage can be estimated. And this is actually binarized here, saying, oh, yeah, there is a significant advantage or not. And the value function that is needed here. Yeah, so if you just copy the behavior, we don't need to say what is good or bad. We just copy it. But for reinforcement learning, we need to say what is rewarded. And the reward model here is very simple. It's number of steps to success. Yeah, it's normalized to be between -1 and 0. So 0 means we actually have success. And you see if there is a failure, then this value model says, oh, we actually move further away from our goal that is at 0. Okay, and then the thing that recovers here. Yeah, but of course, it doesn't always work. Yeah, so it may happen that it actually makes a mistake that cannot be recovered in the end. And there is, in this work, 3 different types of tasks. And the setup is somehow simpler. It's a 2-armed tabletop setup. The tasks meaning making espresso, assembling these card boxes and folding laundry. And they make sure they have realistic variability in the tasks. So here you see learned tasks a bit more. And yeah, if you actually apply that method fully, then you see that the throughput, so the number of successful completed tasks per hour is improving significantly. And also success rates are improving. And yes, some people believe in such approaches. Yeah, so recently, Physical Intelligence collected $600 million US on venture capital, and they have a valuation now of $5.6 billion. Yeah, so this is still, of course, at least one order of magnitude less, or maybe 2 orders of magnitude less than like OpenAI or other big players. Yeah? Still, it's a startup, and it's significant money that some venture capitalists bet on such approaches. And of course, data is key to these models. Yeah, so there might be data from the internet, and this is relatively cheap. Yeah, so when you don't know how to perform a task, you may look up a video in the internet and someone shows you, but this is a different body. This is a third-person perspective. The camera is moving all the time, and this is not so easy to transfer whatever this person is doing in that video towards your own action selection. Or you can have egocentric video, so the camera being on the person, maybe doing cooking, as in this example, and then yeah, you are a little bit more in the shoes of the robot already. Yeah, but still it's a different body, different fingers, and so on. The robot may not actually be able to perform that. Or another startup that came out of stealth mode recently is Sunday AI, and I recommend you watching the video there. Is really impressive. They collect a lot of data using gloves that look like the grippers of that robot. And with humans operating these gloves and then having the same sensors there in terms of cameras and the pressure sensors, you can quickly, in many different households, show how to solve the tasks and then transfer that to this mobile manipulation robot. And of course, there is also the approach of direct teleoperation, and this is good because the human intelligence is in the machine, and the human has to restrict all to use all the restrictions that this machine has, but it's expensive. Yeah, so this is our avatar system, and it costs like several €100,000, and transporting it is difficult, and so on. So collecting data is way more expensive using direct teleoperation. And in the end, of course, it will be a mix of all of the above. Yeah, so lots of data from the internet, or maybe from simulation, even more, but also smaller amounts of data that is more directly on the robot side. And I think these vision language action models are an exciting field of research. I can report that we have a compute project on this new supercomputer in Jülich, Jupyter, together with Wolfgang Burgard from the University of Technology Nuremberg and with Rudi from Karlsruhe Institute of Technology. We actually have the objective of training a vision language action model for mobile manipulation, similar to physical intelligence. We need a lot of data. Where does this come from? We need suitable inductive biases to compensate for the relative shortage of data. But I think scaling obviously works. Yeah, so if you throw in more data, if you throw in more compute, you improve. But as you see also with the language models, at some point the internet is exhausted, and there is diminishing return, but exponential increase of costs in terms of data, in terms of compute. So scaling enough alone is not enough. And I do think that, as a human, we can make only limited experience. So our cognitive architecture must be optimized through some meta learning. Yes, so many generations of our ancestors to then quickly learn new tasks from limited experience that we can make in our lifetime. And that's why I think it makes sense to look at cognitive science, for example, and listen to what they tell us, how maybe working memory could select few items, and then we can have our mental simulation and make plans. What would happen if I do that? What would happen if I do that? And also self-monitoring in the sense that, for example, we feel, oh, that would be unsafe. Don't try that out. Or that is a mistake. And we have to do something else. Or here we reach the limits of our autonomy. And that's why maybe we ask a remote human for help. Yeah, so I think it makes sense to learn from that and maybe then come up with more specialized learning architectures that need less data and are more efficient in their inference. Thank you.